Hello there. Well, today we are going to take a look at a couple of new quantities in the world of rotation. They are rotational kinetic energy, affectionately known as Krot, and rotational inertia, abbreviated with a capital I. I'd like to introduce these conceptually, at least the kinetic energy part conceptually, briefly, and that is to ask the question, does a rigid rotating object on a fixed axis have kinetic energy? Let's go back and look at our friends, the bugs on this turntable. And the question is, if I take this turntable and make it rotate on a fixed axis, does it have kinetic energy? This is, by the way, this is a slightly different simulation that FET has. This one's called torque, and so I make it rotate a little differently. Today I'm not going to worry about torque. But I am going to get it rotating by having this force, and when I take my finger off, the force goes away and it keeps on rotating. Well, here's the question. Does this system right now have kinetic energy? I've now asked that like 6 times. Why is that a relevant question? Well, one can make the argument that it doesn't, because the center mass of this thing, in fact, in particular, if I remove the bug, I can't remove the bug. So if I put the bug in the very middle, okay, the center mass of this thing isn't going anywhere. And so one can make the argument, boy, this doesn't have any kinetic energy because it's just sitting there. But on the other hand, there's movement. There's definitely stuff moving here. Even though the disk on the hole isn't traveling across the room, there's stuff moving. And here's another argument, even though this is simulation, of course. If you notice in the lower right-hand corner, there's what looks like a brake from an old bicycle. And what I'm going to do is rub it, I'm going to push it against the edge of this disc, and when I do that, the disc slows down. Okay, the disc slows down and stops. Well, what just happened there, simulation-wise, is that the brake, I use friction to slow this thing down, and the brake and the edge of the disc get warm because of the friction, and energy dissipated by kinetic friction force. And so that gives me a clue. There must have been kinetic energy there because it turned into thermal energy because now the brake is hot and the edge of the disc is hot. The other thing is that imagine a very heavy disc, and if I say, oh, I'd like to get it moving, you can't just, say, oh, start moving. You actually have to put some work into it. You have to use up some energy. On the simulation, all I do is make this force magically appear. But in fact, if you have to get this heavy disc going, you've got to crank at it somehow. You got to put energy into it. So there are a lot of clues here that tell us, boy, this thing must have some kinetic energy. I don't want to leave it running. The bug might get dizzy. Okay, so let's go back and say it looks like a rigid rotating object. We have arguments to say that it does have kinetic energy, even though it's not moving across the room. It's not translating in our frame of reference. So we tentatively say, yes, it does. Okay, how do we decide how much it has? Because, of course, we want to know how much. So we say, 2, how do we quantify that? How much kinetic energy does a rotating disk have? And so what I'd like to do is first of all, consider a simpler situation than the rotating disk. And the simplest situation is, and I showed this in class today briefly, is a string, and a massless string, the best kind, fixed at one end, and at the other end is a chunk of mass m. And this has somehow been made to rotate. So this mass m is going in a circular path. And it is going at a constant speed, and I will mark that with a velocity vector, v. And again, remember the string is massless, and so I say, does this particle moving in a circular path have kinetic energy? And the answer is, why, of course it does. The kinetic energy is equal to 1/2 mv squared. We don't have to say anything about rotation. It's a particle moving, happens to be moving in a circular direction, but it's a particle moving through space. It's translating, and it has kinetic energy of 1/2 mv squared. Okay, fine. But if we now then, though, do something, and that is to introduce a second mass on this massless string. So I'm going to now attach a second mass in the middle of the string. And and it joins the first one in this circular travel. So this second mass, which I will now call M2, which means I should call the first one M1, is traveling in its own smaller circular path. And it's traveling at the same angular velocity as M1, whose velocity I will now call V1. But this is necessarily traveling slower because, of course, they both travel in the same, they go around a circle in the same amount of time, but M2 is going a lesser distance, so it's clearly traveling slower. Does M2 also have kinetic energy? Why, sure it does. It has a kinetic energy of 1/2 M2 V2 squared. Let's go back and fix the first one as M1 V1 squared. So I have now two objects with kinetic energy, and I could be interested in how much I have in total. So I'll do a very sophisticated thing. I'll add them up. The total kinetic energy of my two-particle system is K1 plus K2. Recognize so far we've done nothing we couldn't have done 3 weeks ago when we were studying energy. We could have said each of these things has kinetic energy because they're both translating through space at velocity v. Okay, let's add them up, and let's plug in the actual values we have. We have 1/2 M1 V1 squared plus 1/2 M2 V2 squared. And we could say, that's nice, we're done, that's the total kinetic energy. But what I'd like to do now, net K, total kinetic, what I'd like to do now is to take advantage of something that we know is the case. And because we can simplify these equations a little bit. And what we know is the case is that each of these two masses, they have different V's, but they both have the same angular velocity because they're both traveling around the circle the same number of radians of arc in the same amount of time. And so I'm going to do a little bit of substitution stuff. We learned yesterday the relationship between V and omega. And that relationship is that V equals omega times R. Now I'm using little r. One thing I didn't do, well, okay, well, what is R in this case? Well, little r, of course, stands for however far a particular point is from an axis of rotation. And these two objects each have their own distance from the center. M2, I'll mark this one first, is R2 from the center. And M1 is R1 from the center. They're each a different distance from the center. So what that means is I can write two separate equations. V1 is omega times R1, and V2 is omega times R2. Notice I'm not subscripting the omegas because they both have the same angular velocity. I don't need to subscript it. I think I would like to sub these into this kinetic energy equation. So I shall 1/2 M1. For V1, I will sub in omega R1 quantity squared plus 1/2 M2. And for V2, I sub in omega R2 quantity squared. Let's square those bad boys. M1 omega squared R1 squared plus 1/2 M2 omega squared R2 squared. Okay, so far what we've done is just take something reasonably simple and make it appear more complicated because it has more terms. How is this useful? Well, it's useful because I'm going to look at each of these kinetic energy terms. This is the kinetic energy of the first mass, and this is the kinetic energy of the second mass. And I'm going to examine the terms in each one. Each one has a mixture of terms, some of which, like the mass and the distance from the axis, that are particular to that one object. And then other terms, like omega, that are this common for each. Those being common, let's factor those bad boys out. In fact, the 1/2 is common as well. So let's do a little factoring. And so that gives me the total kinetic energy is equal to, I can factor out a 1/2 omega squared. And then I'm left with m1r1 squared plus m2r2 squared. Okay. So basically what I've done here is I have removed terms that are particular to each object, and those are in the parentheses, and the terms that they share in common, which are the number 1/2 and this angular velocity, I factored out. All right. Now what I'm going to do is I'm going to take what's inside the parentheses and give it a name. The name I will give it, and in fact, I recognize that one of these terms refers to mass 1 and one refers to mass 2. And I'm going to call these things, define them to be the rotational inertia of M1. The other one, of course, is the rotational inertia of M2. So this is a defined quantity, and we're going to have it make more conceptual sense in another day or two, but for right now, we can simply say that what we're doing is some bookkeeping to pull out from the kinetic energy equation the quantities that have to do with each individual mass and the omega, the angular velocity that they both share. This would not be a self-respecting quantity if we didn't give it a name. I'm sorry, we give it a name if we don't give it an abbreviation, and as you already know, the abbreviation for this is I. And so I can now rewrite this as net K is 1/2 omega squared times I1 plus I2. And so then if I redistribute, I can say this is 1/2 I1 omega squared plus 1/2 I2 omega squared. One might say, why did I bother doing the factoring in the first place? Well, what I want to, and that would be a very fine question, but what I want to point out now is that what I have here are a couple of terms, one for the first object, one for the second object, which are what? They're kinetic energy. They are completely equivalent to the kinetic energy terms we had way up at the beginning, which were just 1/2 mv squared for each one. So we haven't changed the quantity. This is plain old vanilla kinetic energy. All we've done is we've given it a new name. Not even a new name, it's kinetic energy. But we've defined it now in terms of other quantities, one of which is angular velocity, and the other one is this rotational inertia term, which is a quantity that has numbers in it that are based on characteristics of that mass. In this case, its mass and where it is with respect to an axis. So, okay, I want to make 3 points, I think, if I can count, about what we've done here. Okay, one is that we have defined this quantity, rotational inertia. We have an equation for it, which is mr squared. However, this equation is only valid for a point mass. And keep in mind that I cannot in class, I cannot hold up a 3 kilogram ball and say, what is rotational inertia of this 3 kilogram ball? Because all I've given you is m. Rotational inertia is a quantity that is defined with respect to a particular axis, a particular reference point. So I would say, what is the rotational inertia of this ball with respect to some point 2 meters away from it? So, okay, that's one thing about this quantity. Two, one could say we've defined a new quantity, rotational kinetic energy, which is 1/2 I omega squared. But this is actually not a new quantity. This is plain old kinetic energy. We're just looking at it. We're writing an equation for it using different terms. This is really the same as plain old kinetic energy, which we will be calling translational kinetic energy, by the way. So if it's the same thing, why do we have 2 names for it? Just to try to mess you up, I guess. But we're just calculating this same quantity using different things that are probably easier to get. The third thing that I want to point out is that if I go back and look at my silly 2 balls on a string system here, M2 and M1 tied at different points on a string. And this is really where rotational kinetic energy becomes relevant. If I say, what is the rotational kinetic energy of that system? Then what I can do, it is, by the way, this term right here. This is the rotational kinetic energy of the system. But now what I'm going to do is one more definition, I suppose, and that is to say that I of the system, this rotational inertia quantity, is equal to the sum of the individual ones. So in other words, instead of saying, what's the rotational inertia of mass 1 and what's the rotational inertia of mass 2, I can say, what's the rotational inertia of the system? And it is the sum, so I can write it this way, the system is the sum of the individual rotational inertias of the individual parts. You might see what's coming, because what we'll be doing in a couple of days is, instead of having our system be a collection of point masses, we'll do something like, okay, what if we have a stick, something very dramatic like a stick, like a fan blade or something, where the axis is in the middle, and this stick is rotating around the center like that. And if I say, what is the rotational inertia of that stick, that's going to be a very relevant question to ask. And we're going to say, oh, well, the rotational inertia of that stick, the system which is that stick, is the sum of the rotational inertias of all the individual parts that that stick is made of. Well, how is a stick made of individual parts? Well, it would be made of individual parts if we feed it through the calculus Cuisinart and divide it into an infinite number of, or almost infinite number of point masses. Then we can find the rotational inertia of that stick by adding up all the individual rotational inertias of all the little tiny pieces by using integration. So you see that coming up in a couple of days, and that's going to be fun. So get your hopes up for that. The very last thing I want to say is this, and I just want to remind you of a problem that you do not want to get caught up in. If I take a pendulum, okay, which is going to be a ball on a string, and it's fixed at the axis, and I hold the pendulum horizontal, and I say, okay, the pendulum at this point, let's say this thing, it's a mass of m, length l, and I'm going to let it swing down through its lowest point. And so I'm going to define the height y is equal to 0. And we're going to be doing conservation of energy problems with rotation, but this is the point I want to make right now. If I release this pendulum and let it swing down through the lowest point, I would say, oh, I'm turning gravitational potential energy into kinetic energy. And we've done this, of course, 1,000 times. And so the potential energy, if I define y0 at the bottom, all turns into kinetic at the bottom. Okay, this is the warning I want to give you right now. And that is, if we do a problem like this, recognize, please, that it would, what am I trying to say? Don't say that that this potential is turning into, boy, is it turning into rotational or translational kinetic energy? Because here's the thing, it's turning into kinetic energy. And so if you choose to call it translational kinetic energy, then you would say it's turning into the 1/2 mv squared. Alternatively, okay, you can say alternatively this is translational. You can say, oh, I choose to look at this instead of a point mass moving, translating along this curved line. Instead, I choose to look at this as a mass that's rotating around an axis. So instead, I can call this rotational kinetic energy and say it's 1/2 I omega squared. It doesn't turn into both. It doesn't turn into sum of each. They're both the same thing, and you're going to get the exact same answer in each case. It just depends on what viewpoint you choose to take. Do you choose to look at this as a rotating thing around the fixed axis, or do you choose to look at it as a point mass translating in a curved line? Make your choice, choose one or the other, and you're going to, either way, you're going to calculate the correct speed at the bottom, or whatever it is that you want to try to find out about it. Rotational kinetic energy is not a new quantity. It's just a new way of labeling plain old translational kinetic energy. We use it when it's much more convenient to measure I and omega instead of m and v. Thank you.